Okay, thank you. Yeah, thank you very much for inviting me, especially since I feel a bit of an outsider. I was told to give this talk for physicists. I'm not sure what it means. I try to avoid things which I find too technical, but please feel free to interrupt whenever you feel like. And the goal for today would be to say a few things about the moduli space of stable maps, and then say something about these reduced or defined reduced Gromov-Witten invariants. And so maybe I'm not sure, but I imagine that a setup that is familiar is that you may be interested in looking at X to be a Calabi-Yau threefold. And then I understood that this function has some. So I look at Gromov-Witten invariants of some X over G. That I understood that this has a physical meaning that I don't know. I don't know about. But what I'm going to discuss about is this thing here. So I understood that this is the free energy of a type A topological string. And I think that's pretty much all that I can say about the physics of the object that I'm talking about. And so for me, this I will be in a setup which is a bit more general. So for me, X will be some smooth space, so complex space. Probably projective variety. Don't worry too much about that. I will fix some positive numbers, and I will fix a homology class of a curve inside X. And what I'm interested in is to look at all curves of genus G in X of type beta. So and I'll be looking at a space which is written in a complicated way. So this will be something. So I will look at a space which parameterizes curves with some points and a map. And I will have that C is a nodal curve, complex curve, so they look like surfaces. Xi are smooth points. F is a map from the curve to X, such that, so I may look at, so I have a map and I have a, so I have a curve and I have a map from the curve to X, so it makes sense to look at the image of this curve and look at the homology class in X, and I'm asking that this is beta. And I will also ask something which I call a stability condition. So I will look at a space which is parameterizing objects of this type up to some isomorphism. I will not worry too much about this. And the stability condition is something which says that any contracted component of C of genus either 0 or 1 has at least either 3 or 1 special points. So I'm thinking of this okay, so I will have a curve. So these are complex curves for me. I don't know, something like that. And I'm mapping this to X. And now I'm sorry, but I will draw the images as curves. This is a bit confusing, but this is something we usually do. So I'm thinking, in my mind, this is some curve with some components, and this has, I don't know, here I drew a genus 1, here I drew a genus 2, a genus 1, a genus 0, and I have some points. And this is mapped somehow. So for instance, I can completely contract this component because it has 2 mark points, so I don't know, x1, x2, and a node. So this is something allowed. And I'm looking at the set of all such objects. And the claim is that this set has actually a lot of structure, and this MGN of X and beta is compact space. And by space, actually, I mean something which is called stack, but it doesn't. I will not worry too much about that during this talk. Are there any questions about this? So far I have a space X, not necessarily a Calabi-Yau threefold, any space which is, so for me is decent enough, so it's to be something given by zero loci of polynomials in some projective spaces. And I'm looking at the set of all such maps. And this is this set has a lot of structure, and the space is called the moduli space of stable maps. So this is called the moduli space of stable maps. Does it make sense? Okay. So geometrically, this is something which is which we usually like. So there are some good news and some bad news. And the good news is that sometimes this is a very nice space. So for instance, if I look at curves of genus 0 inside the projective space, so to give a homology class, it just means giving a degree. So I will denote it by d, not by beta. And this is smooth and irreducible. Okay, so one thing, so now that I have, so if I have a nice space like this, I may start to play with it. And one way in which I can play with it is, so for any x now, I have some maps which are called evaluation maps from this MGN x and beta to x. So namely, remember that points here are curves with x1, xn, and f. So now I can send this. I take f of some xi. So this will be a point in x. So I have a map which is called the evaluation at the ith point, which is doing this. So now if I have some subspaces of x, zi, I can look at the inverse image of these zi's, intersect them. And if I choose these zi's wisely, I may, wisely. If I choose the codimension in a certain way, I may expect that at some point I will get here a number of points. So the intersection will be a number of points. So if this is zero-dimensional, then the number of points should give the number of curves in X. This is a rather unfortunate place to change the board. Okay, I'll write it here. So curves of genus G, class beta, which intersect Z1, Zn. So for instance, if I look at, I don't know, if I look at the projective plane, and I take beta to be 2, so I look at conics in P2, and let's say that I ask that I take these Zi some, I don't know, 5 points in the plane, then I can ask like how many curves, how many conics pass through 5 points in the plane. I do this intersection here, and the resulting number should be 1, and this gives me an answer to an enumerative question. So the enumerative question is how many curves of this topological type pass through intersect certain subvarieties. Well, this translates into something, into intersection theory on my moduli space of stable maps. So this is a very, if my space is the projective space and if my curves have genus 0, this is a nice situation. And as a mathematician, I like this because it answers enumerative questions for me. And can we do this in general? And the answer is it's much more complicated. And now I've given you the good news, and I will give a list of bad news. Okay, so don't be. Please don't be intimidated. We will overcome all the problems somehow, at least almost all the problems. Yeah. No, so I was not assuming. So for me, X is any projective variety, any dimension. Not necessarily. I will stress it when it's a threefold. So for now, it doesn't have to be a threefold. So in particular, P2, so the complex, the projective plane made sense. I can look at it. Okay, thank you. Right. Okay, so in general, this MGN of X and beta is badly behaved. And so I don't know, if you haven't seen these things, I'm not sure how many expectations you would have. I would have a lot of expectations. So for instance, if I want to have intersection theory, I should have a compact space. So this is important for me. So for this reason, ideally, I would have liked my curves to be smooth. But since I cannot obtain a compact moduli space of maps where the curve is smooth, I add this, I relax my condition, and I'm allowing my curve to have some singularity. So I'm allowing it to have to have nodes. But ideally, I don't want to count these. So in an ideal world, I would just like to count smooth curves. And I would expect these curves with nodes to be somewhere, so in the boundary of my space. Well, unfortunately, this is not true. So for instance, if I look at maps of some genus, so genus greater than 0, to the projective line in degree 1, so I would look at maps. So this will be something. So these will be maps to P1 of degree 1 from a curve of high genus, where if the curve is smooth, there are no such maps. Okay, so the space that I'm interested in is the empty set. And this set is actually non-empty because I can have some, I don't know, for instance, I have, I don't know, G1, GK. So maybe I say that these are contained in here because otherwise I make a more complicated drawing. So I may have, so this would be a projective line is mapped with the identity to the projective line. And I may contract some high genus curves. So for me, curves are always complex curves. So if I were to draw this, I would draw it something like, I don't know, something. Okay, so this is not empty. So this space, it's a very fancy compactification of the empty set, which, I mean, ideally, I would not like this situation, but it's the price that I need to pay for having a compact space. Okay, and even worse than that, I can have something even, I have something even crazier. So for instance, if I look at, so another example would be I look at curves of genus 1 with 0 mark points to the projective plane of degree 3. So these should be elliptic curves, so curves of genus 1 inside the projective space, the projective plane. So I don't know, cubics in P2. But the problem is that this one has several irreducible components. So it looks something like this. I don't know, where I have MP2310, and I'll write here with a 0, and I will call this the main component. And some other components. So what will I have? So I will have one component which is a compactification of smooth curves of genus 1 in P2. So it will look something like I have a genus 1 curve, and I map it to P2, and now I go to the algebraic geometry way of drawing, so this would be something like something given by polynomial of degree 3 in P2. And this is a space which has 9, so if you count parameters of how many curves of genus 1, so in P2 it turns out that there are 9 parameters, so this is a 9-dimensional space. And ideally, I would have liked to have just these. And unfortunately, I also have other stuff. So for instance, I can have this picture where I have, so maybe I draw the image here, so that the image here looks something like most points here will have some, will have the image in P2, which looks like this. But then I have also things like, I have a, does this look colored? Maybe not. Maybe this. And then I also have curves which, so here I have a genus 1 curve. And I have, I glue it to a genus 0 curve. And I send this to P2. But look, my genus 1 curve has one node here, so it has one special point. So I'm allowed to contract this. So I'm allowed to send this to one point. So I'm going to, so I'm sending the genus 0 curve to a degree 3 curve in P2. And this, this extra component, I mean, it's not a mark point. I will send it somewhere. So this is something perfectly legal. I have points like this in my moduli space. And the claim is that if I count parameters and to see how many of these sort of maps I have, it turns out that this is a 10-dimensional space. So the image of something like this would be something like this. And then with the same recipe, I also have something else. So this was one, but I also have, well, I have my genus 1 curve, and I can glue it to two P1s, and I send this in P2 to a conic and a line. And this red curve, I can send it either to this point or to this one. And it turns out, so this is something, and again, I want to know how many such things I have. This is something which you can actually compute. So it's, so this is another space which has dimension 9. Yeah, so if I look at how many and I think you're allowed to I think you're allowed to move the points on the curves. Yes, the nodes. So that gives you the extra dimensions. Yeah, so this one is easy to compute. The first one is also, it's like polynomials of degree 3. Generically, those would give you elliptic curves. This one, maybe you need to know something in order to compute it. Right. Okay. So if I had to draw this here, I would draw it as, this is my plane, and I draw it something like this.
Just to help me understand.
Yeah, sure.
Could you describe the stable maximum detection and stable maximum?
Yeah, so actually, yeah, this is interesting. So the things here are when this thing acquires a cusp. So it's something like this. And yeah, it's a very good question.
So it requires the cusp and the elliptic curve maps.
Yeah, and the elliptic curve maps to this point. Yeah, thank you. You could also have 3 components, but it ends up somewhere in the boundary, so that does not lead to an extra component.
So the stable curve is, what's the domain of the stable curve? It's still.
So the domain is, I mean, it has to be here. So the domain is still this thing. And it's mapped, the rational curve maps here, and this red thing is mapped to the cusp.
And how do you think of that as a stable map in the first?
I mean, here I said that it's the closure of something like this. So I just see that, I don't know, if you have you can have a family of smooth elliptic curves, and then it degenerates to, if you look at the stable degeneration, it will have an elliptic tail. And if you contract this, then you end up with the cusp. So yeah, of course. I mean, of course. So this is the generic. Like most points look like this, but not all points look like this. And on the boundary, I have some other things. So I've given you like the generic point. Okay, thank you. Okay, does it make sense? Okay. So okay, and some other thing which is not exactly what I want, but it may happen. There are what is called multiple covers. So for instance, I can have I'll draw the simplest curve which I know how to draw. So this is a 2-to-1 cover, but it can be any D-to-1 cover. So if I have a map like this, remember that I needed that F push forward of C is my class beta, but here it's, since this is a, I don't know, D-to-1 cover, this will be the image times the degree of the map. So the image of the curve that I get here will have actually a lower degree. And so we also count it's lower genus curves, and also lower degree curves. Maybe I erase this. Right, and there is one technical gadget that I will not say much about, but these spaces, MGN, X, and beta, have an expected dimension. I will call it a virtual dimension. So this is just in this case, this virtual dimension would have been 9, so this would have been the dimension of the space which is compactifying my smooth curves. It's not always the case, but it sometimes is the case. And this is a number which is 1 minus g, the dimension of x minus 3, minus the canonical. So this is canonical class intersected with the curve class. This is this will be a number plus n. So in particular, notice that if X is Calabi-Yau threefold, then this virtual dimension is, well, this one disappears because it's a threefold, and this one disappears. And if I also put n equals 0, then the virtual dimension is 0. And in practice, the actual dimension is always bigger than the virtual dimension. So here you saw that we have a component of dimension 9, and we have some other component of dimension 10, and some other component of dimension 9. And there is something called, so there is a, so these spaces have virtual classes. So this will be something denoted like this, MGN X and beta, virtual. So this will be a class in homology twice this virtual dimension of MGN X and beta. And this has some good properties. And I will not go into this, but it's some device which allows me to do intersection theory on these spaces which are not manifolds. So it's a black box that allows me to sometimes pretend that these spaces are manifolds. And then for me, Gromov-Witten invariants are, so maybe you want to denote it like this. So I fix some homology classes of X such that, maybe call this Ki, such that the sum of Ki is twice the virtual dimension. And so these are homology classes on Mg and X and beta. And I pair them with this homology class. And these will be some rational numbers. And as I said before, these do not count curves with the specified topological data that I fixed, which pass through these, because they also count some extra junk. So they also count some curves potentially of lower genus and potentially also of lower degree. And there are some better invariants. Which are defined recursively in terms of Gromov-Witten invariants. And I'll write like more correct counts, so like, I don't know, better counts. And ideally, we would have liked these. We would have liked to have a similar story, like we have some moduli space and we do intersection theory on it, and that should give us these better counts. And actually, there's a paper on arXiv which appeared yesterday, which seems to be doing that in most of the cases. It's been a struggle to define these Gopakumar-Vafa invariants like this, like with the moduli space. There are some attempts, so maybe mention Maulik and Toda, and previous work by Kim Lee. I will do a bit less. So from now on, we want invariants with the correct genus. So as in the example that we've seen with the curves of genus 1 in P2, I would like to, ideally, I would like to do intersection theory on the main, on that component which was compactifying smooth maps. So maps with smooth domain. But the problem is that I'd like, I mean, there I can do it, but if I want to generalize my space to some, I don't know, let's say the quintic threefold, I'm not, I need this gadget which is called a virtual class. And it's not that I can take one component and define intersection numbers on that. I need to do some extra work. And what I want to do from now on, I'd like to get rid of these components, but in a way that I can still define intersection theory on some good components. So, okay. So these were like reduced invariants were defined in genus 1 by Zinger. There are many papers. And in genus 2 by Hu, Li, and Liu. And this construction was actually something very, very complicated. And it did not, it was, so this is a story which is like kind of 15 years old. And this is very recent, and then there was nothing. Maybe just to tell you how these are related. So the Gromov-Witten, so now if I have X a threefold, it doesn't have to be Calabi-Yau. And I look at Gromov-Witten invariants of genus 1 of some beta of X. These are something which I will define in genus 1 plus Gromov-Witten invariants of genus 0 beta of this X. Sorry, I forgot the X here. So if you have the picture that with 1/12 here. So this is doing a bit less than what these ideal invariants are doing, because these are also discarding multiple covers. These, if you have the picture in mind with the three components that we had for cubics in P2, this is telling me that if I count, if I do intersection theory on the moduli space of stable maps, I get some honest genus 1 curves and some genus 0 curves weighted with some coefficient. And what I want to do is to define something, to define these things here, somehow intrinsically. So I... So the construction is in any dimension, but the formula is just it is just for dimension 3 because it's hard to, so I don't, maybe there is something in, I'm not sure I know how the formula looks in it's a more complicated formula, I don't remember it. I'm not sure how general it is. Maybe there is a formula for any x, but it's complicated. So, because you don't just get classes, so you don't just get invariants, you get some classes on the moduli space of maps. And yeah, it's definitely something I cannot remember. It's a long thing. So, yeah, sure.
This one is still rational number value or integer value?
Good question. So if so, you're asking me this one if it's an integer. So if x is Fano, it's an integer, and if it's a Calabi-Yau, I don't think it's an integer, because you still have the multiple covers that you need to subtract to make the situation good again. So yeah. Okay. So I still keep this. Okay, and I'd like to do it in general. And so here it will get a bit technical. Feel free to stop me.
Also the problem of multiple covers.
Yeah.
And are you going to take care of the different components part while keeping the multiple cover part?
Yeah, exactly. So I'm not going into that.
Usually, if it's a multiple cover, okay, maybe I'm too optimistic, but usually there is a risk like this formula. With summation, usually you can disum it.
I mean, the formula is easy to, usually it's much easier to conjecture things than to define things.
Yeah.
And
but is there, maybe what I'm asking is there a conjecture formula to extract a nice?
yeah, sure. I mean, for threefolds, yeah. I mean, it's, I didn't write it because I cannot remember it. It is the Gopakumar-Vafa formula. So, and you know what are the multiple covers. You know what are the contributions from these other components, like lower genus components. And when you put them together, you get the Gopakumar-Vafa formula. So yeah, that's all that is in trying to make it more, yeah. I'm trying to come up with a moduli space so that the definition is more intrinsic, not in terms of a formula. But yeah, okay. Okay, so so where am I getting? So we want a smooth main component of the moduli space of M, G, and the projective space. And Okay, so so the thing is that if maybe I'll tell you in the end, but the problem is that if I have some let's say hypersurface of the projective space, so for instance, particular the quintic threefold, I understand that this space has some main component which compactifies the space of maps where the curve is smooth. So that thing we understand pretty well, and I'd like to extract from that some class on the space of maps to some hypersurface. So what I want is some virtual class of the space that I'm interested in. And I cannot, so that does not exist naturally. So what I can do is I can blow up this space somehow so that I can make it smooth. And now I'd like to tell you like, no, so what, I mean, I can tell you what I want. So, okay, so sorry for the structure. I'm answering Vivek's questions. So in GINA 0, we can look at X inside the projective space, a hypersurface. And you can look at maps to X inside maps to the projective space. Okay. And here you have E, a vector bundle whose fiber is, so let's say a hypersurface of degree K. And the fiber is the space of section of F pullback of O of K. Fiber over CF. Okay? And then what you do is you can look at the top Chern class of this E and intersect it with M, PR, and D. Okay? So this is what you do in GINA 0, and you'd like to do something similar. And the problem is, I mean, you still have some sheaf which has these fibers. The problem is this is not constant. And what you'd like to extract some vector bundle out of that so that I can do the same. And in genus 1, when you've blown up enough so that the main component becomes smooth, this E becomes, I mean, the pullback of E modulo torsion, I'll come back to this, becomes a vector bundle. So what you want actually, it's yeah, ideally you'd like a smooth main component. Maybe you don't need that, but you definitely need this to be a vector bundle. Okay, so there is some other questions? Okay, so there is something, so I'd like to reinterpret this to the projective space. So I'm interested in this to the projective space. And I can see that to give a map is the same as giving a line bundle and S0, SR, some sections. So I have again that C is, I'm not changing anything, is a nodal curve. L is a line bundle on C of degree D, and SI are global sections of this line bundle, plus the same stability. So to give a map to the projective space is the same as giving this data here. Okay, if you don't know it, just please believe it. And then I have a map, morphis, to a moduli space, which is just parameterizing curves with points and the line bundle. And the claim is that that MGN in PR and D is an open like Zariski open, so it's I don't know, think a dense open inside I'll be a bit sloppy here. F total space of a sheaf on this peak. So so if I pick a curve with some points and some line bundle here, and I look at what are these the fibers over this over a point like this, well, they are just it's a vector space, and namely, it's the sum from 0 to R of H0 of C and L. So this space is something I don't know, which is kind of easy. And there is a very it's a classical it's a classical fact which I think is surprisingly little known. Which says that so classical fact. So if I have F on Y a sheaf, we can construct Y tilde over Y sorry, maybe I call this something else. Maybe I call it Q before I get confused. Such that P is birational. So it means that these have so P is isomorphic on a dense set. So this is a variety. And the pullback of F, so this will be again a sheaf. I can look at the torsion-free part is a vector bundle. So this was done over some, I don't know, like complex analytic space, irreducible, so rather classical situation. I'd like to do the same over this object here, which is a space which is somehow it's not a classical thing. So it's an Artin stack, and we'd like to do the same over this Artin stack. And so with the yeah, it's kind of immediate. So yeah, so it's yeah, it has a universal property. I mean, okay, I'm lying a little bit. So there is a minimal such thing which has a universal property. And once you have one, you can see that you can put on top of it something else. And when you pull back a vector bundle, it will still be a vector bundle. So this thing is not unique. But there is a unique one which has a universal property, and that glues. So yeah, it's we do this for sheaves on. I mean, we do it more generally, but in particular to this one. So in the end, we get for X inside the projective space complete intersection, we get a virtual class for MGN X beta. And I'll put here a main, so this means that I intersect. So on the projective space, it makes sense to look at. So that has like a main component where the curve is generically smooth, and I intersect that with curves in X. And intersection theory. So intersecting this class with evaluation classes gives reduced Gromov-Witten invariants. And yeah, it is the definition. And actually, as I kind of alluded, you can blow up peak in various ways, but they will give the same numbers. Okay, so the spaces may be different, but the numbers will always be the same. And the I haven't used what? The
SI, what you were using on the extra data, which are the element of X0
the SI.
Yes.
Yeah, no, I did use them when I said. So I said that. Okay. Yeah. So I used it in the when I so I have this MGN of the projective space, and D is an open inside the total space of a sheaf F, and this sheaf over, so this is a sheaf over peak, and I mean I can write it, but I didn't want to So we usually write it like this. I'll write a bit of a lie.
I think maybe short answer is F is the thing whose fiber.
Yeah, so yes, so the fibers over peak are some vector spaces, and this is yeah. So this is the total space of the data, curve and line bundle and sections, is a sheaf over this space, which is peak. Does it make sense?
Yeah, okay. No, but in this discussion, you don't need to assume the paid example.
I mean, L is so the. I mean, it kind of is ample because I'm looking at it's like secretly ample because the L lives on the curve, but it comes from a pullback from the projective space. So it's always a line bundle of positive degree over the curve. So yeah, it's like.
Okay, it's definitely not. No, because some components of the curve is trivial.
Yeah, it can be trivial, yes. It can be trivial, yeah.
Line bundle that will contract some of the components of the curve. Oh, okay. So it is not.
So it's a pullback of an O of 1 over the projective space. But then you forget that you had the projective, so you just remember curve and line bundle.
Okay, so the good components.
Huh?
The good components.
Bad
components.
Yeah, good component is generically ample. So yeah, yeah. So this is a bit of a lie, but it's so over the Picard stack, I have a universal curve, and the universal curve has a universal line bundle. And this is a fancy way of saying that I'm parameterized. I have an object which over peak has fibers which are vector spaces, and the dimension of the vector space so the fiber is global sections of L. And it's a bit of a lie, but it's not too bad. And I'll end up with the conjecture. So so if I denote by R H beta these reduced invariants, and then I have that the Gromov-Witten invariance of, and I say that X is a threefold. So the conjecture is that the Gromov-Witten invariants of G beta of X are the sum over H of some constants C of G R H beta, and the sum is over H for some universal. So this means that it doesn't depend on the, maybe also Calabi-Yau, yeah. It does not depend on the Calabi-Yau threefold constants C of G. I think it doesn't, but maybe I need to check. So yeah. So there is, I mean, there's a more general conjecture by Zinger that's also holds also in the Fano case, and that's more It's more elaborate because the C's depend also. It depend on X, and they depend on H and beta. Yeah, maybe. Okay, I'll stop here, and I'm happy to answer questions. Thank you.
Do you know at least RH beta is a deformation invariant? When that makes sense.
Yeah, they should be deformation invariant once you've. So it makes sense to make a blow up of this Picard stack, and once you've fixed that, you can. It makes sense to have this on a family, and then I would guess yes, but.
Do you have an intrinsic definition of the virtual deformation theory of the quantum complex?
An intrinsic in terms of like geometrically, they have some sort of singularities. No. And I think this is what made things very complicated and why this definition didn't come sooner, because in genus 1 so in genus 1 it's a very straightforward blow up. You blow up curves with one node, with two nodes, and so on. Where okay, skipping some details. And in genus 2, it's a very long sequence of blow-ups in various steps, and they say explicitly what they blow up, and it's very complicated. But if you decide that maybe you don't care about what you're blowing up, then the fact that such a thing exists is quite straightforward. In principle, you could do it, but it looks like a giant pain, so I don't know. I wouldn't want to do it. Yeah.
So yeah, just to get to the C of G, but that's actually C of H, I think the sum over each question depends on the summation over H.
The summation is over, oh yes, yes, okay, yeah, thank you.
Then, compared to the example, is leading C of G is always 1. That is, I think, for component.
C of G,
For example, leading.
the leading one. Yes, so it's, yeah, it's always 1. I've hidden a bit something that, like, in the whole story, I usually impose that the degree is high enough so that there is a main component. If it's not high enough, you can still do something, but we didn't write it that way. But yeah, it should be 1 and with the right assumptions.
H should be less than 2, so no H higher than 2.
Sorry?
So this expansion is sum over H is up to G.
Yeah, always. Yeah, sorry, it's and I assume that the first one is the G one, so yeah. So the question is if this thing that we're doing is the same as the Zinger one in genus 1. So they don't do the minimal one, but the numbers are always the same, and this is easy to see because essentially because this map is birational, so that it's essentially a blow up of peak and Yeah. So if you blew it abstractly, if you blew it up abstractly without blowing up peak and knowing that the blow up comes from there, you wouldn't have that the numbers are the same. But since whatever blow up of peak you're taking, the way the virtual class is defined will not see the blow up. So yeah, the numbers are the same.
If I understand, you're saying that as long as we pull back this F, whatever, as long as we pull back this F to your modulus space, it becomes vector bundle.
Yeah, so the main component becomes a vector bundle. Yeah. So these boundary components are the torsion of this sheaf. Yeah. Okay, thank you. Thank you.